Okay, so in linear algebra, a vector space is defined as a set of vectors that you can get by taking linear combinations of other vectors, right? And in what's a linear combination? Well, there are only two things you can do. You can add two vectors, or you can multiply a vector by a constant number, a constant real number, and then you can add the result to another vector. So just simple multiplication and addition is all you can do to form a set of linear combinations, or a vector space. Okay, so my question is, we can see polynomials or geometric vectors, arrows floating in space. We can see both of those objects as vectors in linear algebra, but the real world versions of those objects behave very differently, and yet we restrict them with these two rules of only multiplication and by numbers and addition. And so my question is, why this arbitrary restriction? Okay, to demonstrate with an example, okay, so take a vector, a geometric vector floating in space, right? So say you have vector A and you have vector B, right? These vectors are linearly independent. They live in different dimensions, right? So by the laws of linear combinations, there's no way you can get B from A, because they just live in different dimensions. Would you agree? However, you can get any vector, any third vector, from combining these two in a linear way. It'll just be locked to that plane, right? Okay, now you have a third vector, vector C. This vector is linearly independent from A and B. So by definition, you can't get C by combining A and B. It's out of reach. It's in another dimension. So that makes a lot of sense to me intuitively. Now let's take the case of polynomials, all right? So let's say we have a polynomial x cubed plus x squared plus x plus 1, okay? You could define a basis with respect to which you would decompose this polynomial. So let's just say it's just the same damn elements of this polynomial, right? You got an x cubed, you got an x squared, you got an x, and you got a 1. So you could easily just add them all together. That plus that plus that plus that to get that, okay? But then, what if your basis was this? X squared plus x plus 1. So you have a polynomial, a third degree, I guess you would say, a third degree polynomial, right? Its highest power is 3, but your basis only has a highest power of 2. So by linear combinations, it's impossible for you to get this polynomial from this basis, right? You can't combine any of these elements. Sorry, there shouldn't be pluses, there should be commas. You cannot combine any of these elements in a linear way to get this. You can't add any of them together or multiply them. There's no real number, 3, 100, 1,000,000, 0.5, that you could multiply by one of these to make it magically become x cubed, right? So by linear combinations, you're out of luck. However, and of course, this is consistent with the geometric vector space, because you can't add these together or stretch them or squish them and then magically get C. It's just totally out of reach in that it's outside of that vector space. Okay? So this makes sense to me. But my confusion is, okay, but then step out of vector spaces, and in the real world, you could easily do this one, x squared times x. And that will get you x cubed, right? X squared times x. You know, just add the exponents and you'll get an x cubed. So you could combine these elements to get this other element in the real world, but we've imposed this artificial restriction called linear combinations. And that's the only reason you can't. However, the same does not go for geometric vectors, because geometric vectors, both by the definition of linear combinations and in the real world, it's impossible to get C from combining A and B. And I know some of you are going to say, oh, we'll just take the cross product of A and B. But mind you, C is not orthogonal to A and B, okay? So I guess you could take the cross product of A and B, get a third vector orthogonal to the AB plane, and then you could decompose. Then you can combine it with A and B in order to decompose C. But to me, that's kind of cheating. That's not the same thing, because you didn't do some weird cross product nonsense with x squared and x to get x cubed. You just multiplied them, and you directly got x cubed. There was no intermediary step. So my question is, why this inconsistency? To me, it just feels like an arbitrary restriction of, okay, vector spaces, you're only allowed to multiply by numbers and add. Why the arbitrary restriction? What am I missing here? And what is the deeper meaning, deeper connection between polynomials and geometric vectors?